So I've got all my pennies. I put them back in the jar. And now I'm going to shake them and mix them all up. Then I'm going to dump them out on the table. The shaking of the jar represented a mixing of the pennies, and it represented a half-life of radioactive decay. The half-life is the amount of time it takes for half, statistically speaking, half of the uranium to decay to lead. So what I'm going to do now is I'm going to take a look and I'm going to organize my pennies into two piles. A pile of heads up and a pile of tails up. Okay, so in this experiment, a heads-up penny represents uranium-235. Uranium-235 is radioactive. It occurs in igneous rocks that form from magma or lava, and it's going to decay to lead-207. So the amount of time it takes for uranium-235 to decay to lead-207, or a population or amount of uranium-235 to decay to lead-207, the amount of time it takes for half is 0.7 billion years. So that's obviously known as the half-life. So again, the pennies that are heads up are going to represent uranium-235. U is the symbol for uranium. 235 is the atomic number of this isotope, protons and neutrons. Pb is the symbol for lead. 207 is the number of protons and neutrons again. So every round, starting with round 0, or the time at which the rock initially formed, the igneous rock initially formed, as we go from round 0 to round 1, 0.7 billion years go by. And as we go from round 1 to round 2, another 0.7 billion years, and so on, all the way down through this process. Alright, so after you've started with 128 pennies and you shook them in the container and you counted them all, what you're going to record here is the number of heads that are still remaining. And so out of 128 to start with, record your actual data. And so let's say that you had 70 heads remaining after the first round. Okay, well, what is the expected number of unchanged pieces? Okay, well, let's think about that. If we started with 128, I would expect half of 128 to be heads. So that would be 64. That's how I would fill out this column. The heads up are the actual number of unchanged pieces, or the parent isotope atoms. These are still considered uranium atoms. The tails up are now considered the lead-207 atoms. And so those are now out of play because they're no longer radioactive. We're no longer considering them for future rounds. So only heads up pennies will continue on. And so only place the remaining 70 heads back in the container and discard any of the tails. Just put them off to the side. This is representing yet another half-life of radioactive decay. In the instance of uranium-235 going to lead-207, this takes 0.7 billion years. That's a lot of time. 0.7 billion years of time for another half-life. Okay? You're going to dump those out again and once again organize them into piles of heads and tails. So after round 2, you had 70 pennies to start with that were heads up, and perhaps at round 2 now we have, let's say, 32 pennies remaining that are still heads up. How many would you have expected? Again, I'm not going to take half of 70, I'm going to take half of 64 for my expected column. So continue filling that out, and that would be 32. So I'm actually right exactly what I would have expected for this. Place the remaining 32 heads up pennies back in the container, shake them again for round 3. Okay. Once again, separate out the heads and the tails, and then count up how many we have that are still heads, and so maybe I'm down to 15 or so. And what is expected? Expected is half of 32, which is 16. So you can continue filling this out. 16, 8, 4, and so on. And continue filling this out with your actual data, whatever you happen to get. Okay, so now let's graph our data. Here we have the actual number of heads that turned up and then the expected. All right, and we're going to graph that using graphical analysis. So I'm just going to bring graphical analysis in, and I'm going to create experiment, and I'm going to select manual entry. All right, so I'm in the table view, and I'm going to go ahead and set up my 3 columns here. The X column is the, here's the X column right here. And so I'm going to tap and hold there, and I'm going to rename that. This is time, just like it was in Lab 0. And the units here are kind of a weird unit, I guess. It'd be half-life. Okay. The second column here, I'm going to tap and hold. I'm going to change that. I'm going to rename it to actual heads. And then I'm going to create a third column. I'm going to rename that expected heads. Very good. And now simply need to fill in all the data. Okay, once I've got my data transferred over from Notability to the graphical analysis app, I don't need a split screen anymore. So I'm just going to open up graphical and work from there. I'm going to view this as a graph, as one graph. Alright, mine didn't automatically come up looking like I wanted it to, so I'm going to have to make a couple adjustments. I'm going to double tap the screen, and that's going to auto scale from 0 to 9. I'm going to select the y-axis where it says actual heads, and I notice that actual is check marked but not expected, so I'm going to make sure they're both checked. Don't check time, but just check actual and expected. Okay. I want lines drawn, so I'm going to select in the bottom left that icon, and I'm going to change the appearance to both points and lines. I'm also going to title this, I'll call it the Half-Life Lab. Half-Life Penny Lab. Alright, so that looks pretty good. Before you do your screenshot, you will probably want to select that so that you can see what your actual is and what your expected is. Or I guess you could just write that down in Notability. It's pretty slick to actually also do a curve fit of this. So not statistics like we did for Lab 0, but a curve fit. You can experiment with which one actually fits well. The natural exponent is a pretty clear-cut winner there. So I'm going to leave that on there too. I think that looks pretty good. Alright, so maybe that would be my screenshot. And then I'm going to go ahead and put that into Notability. I'm just going to, this is the older version of this write-up. Maybe you'll have a newer version by the time you get this. But I'm going to go ahead and add my screenshot there now. There. Perfect. And then we're going to fill out the chart below concerning the expected results. Okay, so in round 1, number of uranium-235 atoms, remember we're dealing with expected, would be 64. Number of lead-207 atoms, if you had 64 of the 128, so you take 128 minus 64, you're going to have had 64 tails that you would expect as well. Okay, so what's my ratio of uranium-235 to lead-207? Okay, the ratio is 64 to 64, but ratios reduce, so that's a 1-to-1 ratio. Okay, number of half-lives I'm dealing with, it says right at the top here, it says number of half-lives is 1 half-life. Okay, so that's just 1. And then time in millions or billions of years. Okay, so remember that the time we're dealing with for 1 half-life is 0.7 billion years. So time 0.7, I'll just do 0.7b, I'll do 0.7. Okay, so let's take a look at the next column. Round 2, 2 half-lives. Okay, well, a half-life definition is you're going to end up with half of what you started with. So if we had, well, remember we started with 128. That was at round 0. And then at round 1, the 128 split to 64. And now 64 is going to split again to 32. Well, we can go this way too. 32 is going to split again to 16. 16 is going to split again to 8. And then obviously 4. And here, our equation remains the same. So we have to take whatever we have here, 128, and we're going to subtract 32. Okay, so we're going to get 96 expected lead-207 atoms. Okay, what about the ratio of uranium-235 to lead-207? What about that? Okay, well, our ratio now is 32 to 96. Okay, that might not seem reducible, but it is. If you divide each of those numbers by 32, it's going to work. So that's going to end up to be a 1-to-3 ratio of uranium to lead. Number of half-lives, well, again, it just says right here 2 half-lives. Okay, well, time in millions or billions of years is 0.7 times 2, which is 1.4 billion years. Okay, so I filled out most of the chart. Go ahead and see if you can fill out the rest of it here using the same kind of logic.